Have you ever stopped to wonder whether the universe really behaves the way your everyday experience suggests? Or whether that sense of order is only an illusion that breaks down the moment you look closely enough? We are used to a world where causes lead neatly to effects, where time moves forward, and where observation simply reveals what is already there. Yet the material in this file invites you to step beyond that comfort. These are not speculative fantasies or mathematical curiosities. They are grounded in real experiments, real paradoxes, and real disagreements among physicists. Together, they challenge not only how the universe works, but how we understand reality, time, and even our own place within it. Most of the time, the universe presents itself as something stable and dependable. You learn that observing a system can alter the very thing being observed. At first, it is tempting to dismiss this as a quirk of mathematics, an abstraction that exists only on paper. Perhaps it is strange only in equations, not in the real world. But when you examine the evidence more carefully, that comfort disappears. These phenomena are not speculative. They have been tested, repeated, and confirmed again and again, and they remain deeply unsettling. They are not confusing because we have failed to investigate them thoroughly. They are confusing because, despite decades of effort, there is no agreement on what they truly signify. That is the heart of this discussion. It is not about the superficial idea that quantum physics is odd or counterintuitive. It is about the genuine paradoxes, the ones that have persisted for generations without a clear resolution. These are the problems that trouble physicists late into the night, because if they accurately describe nature, then our picture of the universe may be fundamentally flawed. When most people hear the word paradox, they imagine a clever riddle or a playful logical trick, something curious but ultimately harmless. In quantum physics, paradoxes are nothing like that. They are not intellectual games. They expose a profound fracture in our understanding of reality itself. In the realm of classical physics, the world behaves sensibly. Throw a ball and it traces a definite trajectory. Flip a switch and a light turns on. You might lack complete knowledge of every influence, such as air resistance or the precise flow of electricity, but the underlying reasoning holds together. Nature behaves in a consistent and predictable fashion. This is the framework within which Newton built his laws, and later Einstein refined them with relativity. Every effect had a cause. When something occurred, there was an explanation. That sense of clarity began to dissolve when scientists turned their attention to much smaller scales, to atoms, electrons, and photons. What they found was not merely a set of more intricate rules. They found behavior that defied intuition. The difficulty was not missing information or hidden variables waiting to be discovered. Even with complete knowledge of a system, certain outcomes could not be foretold. Only probabilities could be assigned. This realization gave rise to quantum mechanics. It offered a new language for dealing with uncertainty. Instead of declaring that a specific event will occur, it tells us that an event may occur with a certain likelihood, and remarkably, it succeeds. Quantum theory stands as one of the most precise and effective scientific frameworks ever devised. It underpins the technology of the modern world. It makes possible our electronic devices, lasers, medical imaging scanners, and navigation systems in orbit around Earth. Without it, contemporary life as we know it would simply not function. And yet, there is a troubling catch. Despite its extraordinary practical success, we do not truly grasp what the theory is telling us about reality. The mathematics predicts behavior with astonishing accuracy, but it remains silent on the deeper question of what these particles actually are, or why they act in this peculiar manner. When we attempt to answer those questions, we collide with paradoxes. We encounter situations in which different aspects of the theory appear to clash, or where the implications seem logically impossible. These paradoxes are not trivial inconveniences. They signal that something essential is missing from our understanding. Imagine owning a device that performs flawlessly most of the time, yet occasionally displays inexplicable symbols on its screen. It still functions, it still does its job, but you cannot ignore the feeling that something deeper is going on. That is what quantum paradoxes represent. They are interruptions in the narrative we use to explain how the universe operates. One of the most troubling issues centers on measurement. In quantum mechanics, a system can exist in multiple possible states simultaneously, a condition known as superposition. From a practical perspective, this is manageable. When we measure the system, we observe a single outcome. But the deeper question remains unresolved. What exactly constitutes a measurement? Is it a machine? Is it a conscious observer? Does the universe somehow recognize the act of observation? At this point, the clarity dissolves. From that uncertainty emerges a host of bewildering scenarios. Particles appear to settle on a particular behavior only when we look at them. Systems seem to respond differently depending on whether they are observed. In some experiments, the result appears to depend on choices made after the event has already occurred. These ideas are not hypothetical musings. They arise from real experiments, carried out repeatedly, with consistent results. And each time, they leave physicists uneasy because they challenge our most deeply held assumptions about time, space, and causality. To make matters even more unsettling, there is no single interpretation of quantum mechanics that commands universal agreement. Some physicists argue that the wave function, the mathematical description of a quantum system, is merely a computational tool for predicting probabilities. Others believe it corresponds to something physically real. Some suggest that every measurement causes the universe to branch into multiple realities. Others maintain that everything unfolds deterministically, and our uncertainty is simply a reflection of incomplete knowledge. Some have even suggested that consciousness itself may be involved in narrowing countless possibilities down to a single reality. This sense of unease was felt deeply by the great figures of physics. Richard Feynman once remarked, with characteristic candor, that nobody truly understands quantum physics, an acknowledgement of how slippery its essence really is. Niels Bohr went further, insisting that anyone who encounters quantum mechanics without feeling shock has almost certainly failed to grasp it. Roger Penrose, never one to soften his words, stated plainly that quantum mechanics makes no sense at all. Albert Einstein, troubled by where it seemed to lead, cautioned that if it were correct, it might signal the end of physics as a proper science. And Erwin Schrödinger, whose own mathematical work helped ignite the revolution, confessed that he disliked it deeply and regretted ever becoming involved with it. Taken together, these voices remind us that quantum mechanics is not merely a technical riddle waiting to be solved. It is a reflection of the boundaries of human understanding, a confrontation with limits we may never fully overcome. For now, we measure what we can, we stand in wonder, and we stumble forward, suspended between fascination and frustration in a universe that stubbornly refuses to obey our intuitive expectations. These disagreements are not just abstract debates among academics. They expose how little we truly understand about reality at its most fundamental level. Quantum paradoxes force physicists to face that unsettling truth. They are like fractures in a wall. You can cover them with fresh paint, but they remain beneath the surface. Ignore them for too long, and you begin to wonder whether the entire structure is as stable as it appears. That is why these paradoxes haunt scientists. It is not simply that the answers are elusive, it is that the questions themselves undermine the very way we define what is real. Each paradox serves as a reminder that the universe may not operate according to the mental frameworks we have built for it. Perhaps our theories are incomplete, or perhaps we are asking entirely the wrong questions. That is precisely what gives paradoxes their power. They are the universe whispering, or perhaps shouting, that our work is not finished. Before moving on, let me show you something curious. Think about how inspiration works. You can have a brilliant idea, fully formed in your mind, yet the most difficult part is bringing it into the world. You start thinking about websites, visual identity, layout, hosting, and suddenly you find yourself wondering whether you truly have the time or energy to manage it all. This is where ODU enters the picture. It is not merely a simple website builder, it is a complete business platform designed to grow alongside your ambitions. In 4 straightforward steps, your site can be live and ready. You choose your type, your industry, and your goal. You select your colors or upload your logo. You add the pages and features you need. You pick a theme, and you are done. From there, everything becomes a matter of dragging and dropping. There is no need to touch code. There is no need to search endlessly for instructions on how to change a section. You simply move elements around, replace images, adjust layouts, and shape the site exactly as you wish. The first application you select is free for life. That includes unlimited hosting, full support, and no silent countdown ticking away in the background. You also receive a free custom domain for your first year, so from the very beginning your site looks credible and professional. If you are trying to launch anything at all, Odeo removes many of the usual obstacles and makes the process far simpler. Now, let us return to quantum mechanics, and to one of its strangest and most misunderstood ideas, the delayed choice quantum eraser. It is not as famous as the double-slit experiment, but it is best thought of as its more disturbing sibling, increasingly unsettling the more deeply you understand it. To see what is happening, imagine firing a single photon, a particle of light, into an experimental setup where it has two possible paths, perhaps created by mirrors or slits. If you do not measure which path the photon takes, something remarkable occurs. The photon behaves like a wave. It is as though it travels both paths at once, producing an interference pattern, much like overlapping ripples spreading across water when two stones fall into a pond. However, the moment you place a detector to identify which path the photon followed, the interference vanishes. The photon now behaves like a particle, committing to one path alone. It is as if acquiring information about its journey forces the photon to abandon its wave nature and choose a single route. That alone is strange, but the quantum eraser experiment pushes the idea even further. Instead of deciding whether to measure the photon's path before it reaches the screen, you postpone that choice until after the photon has already arrived. You let it pass through the apparatus, strike the screen, and only afterward decide whether to preserve or erase the information about which path it took. This is where the experiment becomes truly unsettling. If you choose to erase the path information after the photon has already hit the screen, the interference pattern returns. It appears as though a decision made in the present is influencing the behavior of the photon in the past. To be precise, nothing on the screen physically changes. Each photon remains exactly where it landed. Yet when the data are analyzed and sorted according to whether the path information was kept or erased, two distinct patterns emerge, one displaying interference and one without it. And what determines which pattern you see is a choice made only after the event itself has already occurred. This is not some peculiar act of stage magic. It is a genuine experiment, performed again and again, using photons and many other particles, and each time the outcome aligns precisely with what theory predicts. Whether information about the path exists or does not exist, even when that choice is made later, determines whether the behavior we observe is wave-like or particle-like. And that immediately raises a profound question. How can an action taken now have any influence on something that seems to have already occurred? Does that not violate causality? The answer is no, not in the way you might fear. This arrangement cannot be used to transmit information into the past. The interference pattern only becomes visible when we collect vast amounts of data and then sort those results according to how the path information was treated. There is no way to use this to send a signal or to foresee what will happen next. And yet, the simple fact that a present decision reshapes the statistical appearance of the past is deeply unsettling. Some physicists suggest that a particle does not possess a definite history until we ask a question about it. Others argue that the wave function holds every possible outcome until the final interaction takes place. There are also interpretations that hint that time itself may not function as we intuitively believe. Perhaps the past, present, and future are not truly separate, but merely different perspectives within a single, unified structure. Or it may be that what we call the past is nothing more than a record, one that is continually rewritten by events unfolding now. There is no agreement on which explanation is correct, but there is universal recognition that something about our classical intuition has failed. In the everyday world, such a scenario would be unthinkable. Imagine throwing a basketball through a hoop, watching it pass cleanly through, and then later deciding whether you actually observed it. And somehow that later choice alters whether the ball went in at all. That is the scale of strangeness we are confronting. The quantum eraser paradox offers no neat resolution. Instead, it disrupts our assumptions about time and observation. It tells us that observing is not a passive act, it is an active one. Observation does not merely uncover information, it plays a role in selecting which version of reality becomes fixed. And that is not only strange, it is profoundly disturbing. Because if choices made in the present can influence the past, even if only in subtle statistical terms, then what does that imply about the nature of time? Is the past something rigid and unchangeable, or is it another layer of probability, waiting to be refined? In most physical experiments, we assume a single shared reality. When something happens, it happens for everyone. When a measurement is made, all observers agree on the result. But the Wigner's friend paradox challenges that assumption. It poses a simple yet deeply troubling question. What if two observers witness the same event and disagree about what is real? This thought experiment was proposed by physicist Eugene Wigner in 1961. He imagined a scenario reminiscent of Schrödinger's cat, but with an important difference. Instead of a cat in a box, there is a human observer, Wigner's friend, inside a laboratory measuring a quantum system. Suppose the system is a particle in superposition, existing as spin up and spin down at the same time. Wigner's friend performs a measurement and records a definite result, perhaps spin up. From the friend's perspective, the measurement has collapsed the superposition into a single outcome. The particle no longer occupies both states. It now has a value. Reality, as far as the friend is concerned, has become fixed. But now consider Wigner himself, standing outside the laboratory, unaware of the result. From his perspective, the entire lab, including his friend, remains part of a quantum system. He has not observed anything yet. To him, the laboratory is still in superposition. The particle exists in both states, and because the friend has interacted with it, the friend is also part of that superposition, having observed both spin up and spin down in different branches of the wave function. This is where the paradox truly emerges. Both Wigner and his friend have followed the rules correctly. The friend made a valid measurement and saw a clear outcome. Yet from Wigner's point of view, that measurement has not occurred. He must describe the entire laboratory as a single entangled system, still suspended in superposition. So who is right? One observer experiences a definite reality, the other perceives a spectrum of possibilities. And this is not merely a question of knowledge or ignorance, it is a question about what actually exists. For many years, this remained a purely theoretical puzzle. It was easy to argue that it did not matter, because we cannot place human beings into quantum superposition. But in recent years, physicists have devised ways to test simplified versions of this idea using particles and detectors. In 2019, a study published in Nature Communications demonstrated that under certain quantum conditions, two observers can indeed record different realities. These are not differences of opinion or errors in measurement, they are genuine physical outcomes. One observer records one result, another records a different one, and both are correct within their own framework of events. This forces us into unfamiliar territory. In classical physics, reality is singular and objective. If two people disagree, one of them must be wrong. But quantum mechanics suggests that this assumption may no longer hold. The Wigner's friend paradox invites us to question whether reality itself might depend on the observer, not merely in the sense of personal knowledge or individual viewpoint, but in terms of what genuinely takes place. Certain interpretations of quantum mechanics attempt to address this by proposing that every observer inhabits their own version of the universe, a private strand of reality. This idea aligns naturally with the many worlds interpretation, in which every possible outcome occurs, and each observer experiences only one particular branch. From that perspective, Wigner's friend settles into one version of reality, while Wigner himself settles into another. Both descriptions are valid, yet they belong to different worlds. Because they no longer occupy the same reality, complete agreement becomes impossible. They are both right, but not within a shared universe. Other interpretations take a different route and suggest that measurement has nothing to do with collapsing a wave function. Instead, it is about updating information. What changes is your knowledge of the system, not the physical system itself. In this view, nothing truly collapses. Still, this leaves room for different observers to hold different information about the same system. Even so, the paradox does not disappear. At some stage, those two observers will compare what they know. When that moment arrives, whose account prevails? This is what makes Wigner's friend so unsettling. It forces us to ask whether reality is real in the way we usually understand it. If two observers can experience different outcomes from the same event, then what does it actually mean to say that something happened? Can we still speak about objective events, or are we each confined within our own branch of perception? Consider how this might extend beyond the laboratory. Picture two people watching the same event, perhaps a coin toss. One sees heads, the other sees tails, and both are correct within their own frame of reference. Not because one is lying, not because one remembers incorrectly, but because reality itself divides according to who is observing. That sounds like the language of science fiction. Yet Wigner's friend compels us to entertain the possibility that this is, in fact, how the quantum world operates. The most troubling aspect is that we do not possess a clear resolution. There is no consensus. This is not a failure of intelligence among physicists. It is simply that the rules of quantum mechanics permit this kind of disagreement to exist, and still, we do not fully grasp why. The deeper we explore, the more this thought experiment challenges our understanding of reality, truth, and observation. It suggests that measurement is not merely about reading data. It may actually be about creating the particular version of the universe you experience. Once that occurs, someone else could be living in a completely different version right beside you, and you would never know. Most of us grow up with the sense that time flows in a single direction. One thing happens, then another follows. You wake up, then you brush your teeth, then you step outside. You do not brush your teeth before waking. When you drop a glass, it shatters. It does not leap back together and return to your hand. That is how time feels. A single path forward, without exceptions. But in quantum mechanics, the situation is far less straightforward. The equations that describe how quantum systems evolve over time, such as the Schrödinger equation, are indifferent to the direction of time. They function equally well whether time moves forward or backward. This feature is known as time symmetry. In mathematical terms, if you recorded a quantum process and played the recording in reverse, the equations would still hold. There is no built-in arrow of time within the fundamental laws. At first glance, this might seem unimportant. You could argue that equations may not care about time, but everyday life clearly does. Yet the further you investigate, the more complex the picture becomes. This is because certain quantum experiments imply that the outcome of an event can depend on something that has not yet occurred. This idea is called retrocausality, where the future influences the past. A commonly cited example is the delayed choice quantum eraser, discussed earlier. In that experiment, the behavior of a particle appears to depend on whether you choose to erase or preserve certain information after the particle has already passed through the system. From an everyday perspective, it feels as though a present decision is shaping what the particle did in the past. Retrocausality takes this seriously. It does not merely say that the situation looks strange. It suggests that the particle's earlier state may genuinely be determined by a later event. Perhaps causes do not always have to precede effects. Perhaps time itself is more flexible than we imagine. It is important to be precise here. Retrocausality does not imply that you can send messages to your past self or undo events that have already occurred. That would violate many other principles in physics, and there is no evidence for such forms of time travel. What it does suggest is that the boundary between past and future may not be as sharply defined as we once believed. In some interpretations of quantum mechanics, information flows in both directions. Actions taken in the present can complete missing details of the past, not by rewriting history, but by filling in the picture. This is where the picture becomes far more subtle, because you are now confronted with a universe in which the full account of an event is not complete until both its beginning and its conclusion are fixed. It is rather like attempting to write a novel when you cannot properly understand how the first chapter works until the final chapter has already been written. There are serious ideas in the foundations of quantum theory that explore exactly this possibility, and one of them is known as the two-state vector formalism. In this framework, a quantum system is not described solely by a state evolving forward from the past. It is also shaped by a second wave function that propagates backward from the future. The system is therefore determined by two boundary conditions: what was true at the start and what turns out to be true at the end. That represents a profound shift in perspective. In almost all of science, we explain phenomena by looking backward in time. If you want to understand why an apple fell, you invoke gravity, the tree, and Newton's laws. You do not say that it fell because someone needed to eat it an hour later. Yet within a time-symmetric or retrocausal interpretation of quantum mechanics, that sort of explanation does not sound quite so absurd. Some physicists are drawn to this idea because it sidesteps certain difficulties associated with measurement and wave function collapse. Rather than imagining the wave function suddenly snapping into a single outcome when we observe it, retrocausal approaches suggest that both past and future jointly determine what we see. There is no abrupt jump, only a continuous blending of influences arriving from both directions along the timeline. However, this way of thinking brings its own conceptual challenges. Most notably, it forces us to confront our assumptions about free will. If future events can influence the past, then perhaps our choices are not as unconstrained as we like to believe. Perhaps they are already encoded within the complete structure of space-time itself. That line of thought leads naturally to another unsettling concept, known as the block universe. In this view, time does not flow at all. The past, the present, and the future coexist as a single, static structure. You are not traveling through time, you are simply becoming aware of different cross-sections of a fixed four-dimensional block. For some people, this idea is strangely reassuring, while for others, it is deeply disturbing. What makes retrocausality particularly intriguing is that it does not violate the mathematics of physics. Researchers have examined it from many different perspectives, and it turns out that a wide range of quantum phenomena can be described just as effectively, and sometimes more simply, if future events are allowed to help shape what happens now. Even so, consensus remains elusive. Many physicists continue to favor interpretations that preserve a one-way direction for cause and effect. Others are more willing to entertain the possibility that time itself is an illusion, or at least an emergent concept that only makes sense on large scales and breaks down in the quantum domain. And there are those who suspect that all existing interpretations miss the point entirely, and that we need a fundamentally new way to think about time. Whatever the ultimate answer may be, this aspect of quantum theory reaches far beyond technical physics. It touches the core of how we experience reality. We are deeply conditioned to think in terms of past and future, before and after, cause and effect. Yet quantum mechanics persistently undermines that intuitive framework. Retrocausality does not grant us the ability to build time machines or rewrite history, but it does compel us to rethink the assumption that time is a simple one-way street. Perhaps it resembles a network of roads, some leading forward, some backward, all interconnected in ways we do not yet fully comprehend. And if that is the case, then the question is not only what the past tells us about the future, it is also what the future might be telling us about the past. One of the most extraordinary features of quantum mechanics is the way in which two systems, whether particles, devices, or even people, can appear to coordinate their behavior perfectly without any exchange of signals. There is no communication, no information transfer, and no opportunity to coordinate. And yet, when their outcomes are compared, they match with astonishing precision, not occasionally, but every single time. This phenomenon is often referred to as quantum pseudo-telepathy. To understand it, imagine a simple game. You and a friend are placed in separate rooms, unable to communicate in any way. Each of you is asked a single question to which you must respond with either yes or no. The questions are chosen randomly from a predefined list. The catch is that you both win only if your answers align according to a specific rule. If they fail to do so, you lose. It is a coordination challenge without communication. In the classical world, the best strategy is to agree in advance on a set of responses. You might memorize an elaborate table of possible question pairs and decide ahead of time how to answer each one. This can improve your odds, but it will never guarantee success. There will always be combinations that defeat any classical strategy unless you cheat. Now suppose instead that you and your friend share a pair of entangled particles. These particles possess a connection that is independent of distance and independent of time. When one is measured, the outcome of the other is immediately correlated, whether it is across the room or on the opposite side of the universe. Using this entanglement, you each make your decisions based solely on your own local measurements. You still do not communicate. You still exchange no information. Yet when the game ends and the answers are compared, they align perfectly in a way that no classical explanation can account for. This is precisely what happens in quantum pseudo-telepathy games. Experiments have repeatedly demonstrated that players using quantum entanglement can win such games with a success rate that would be mathematically impossible using any conventional approach. No messages are sent during the game, yet the outcomes reveal a deeper connection linking the results. This is why the effect is described as pseudo-telepathy. It gives the impression of mind-reading or invisible cooperation, but that is not what is happening. No signal is transmitted. No hidden code is exchanged. It is not faster than light communication, because nothing is actually being sent from one player to the other. The entangled systems are simply correlated in a way that defies classical intuition. A famous illustration of this is the Magic Square game. This is a straightforward logical puzzle in which two players must fill a grid with ones and negative ones while satisfying specific row and column conditions. Using classical physics, it is impossible to win every round. But if the players share entangled particles and perform appropriate quantum measurements, perfect coordination becomes achievable. Not because they are cheating, but because the quantum nature of reality allows it to happen. Another illustration comes from the Gigahertz game, named after the physicists Greenberger, Horn, and Zeilinger. In this scenario, there are 3 participants. Once again, they are not allowed to communicate in any way, and yet they are able to give answers that align with one another in a manner no classical explanation can account for. This is not merely a theoretical construct. It has been demonstrated repeatedly in controlled laboratory experiments. So what is actually happening? At the core of this phenomenon lies quantum entanglement. When 2 particles become entangled, they are described not as separate entities, but by a single wave function. They are no longer independent objects carrying their own individual properties. Instead, they form one unified system. Even when separated by vast distances, that system remains intact. When you measure one particle, you immediately gain information about the other. This does not happen because a signal is sent between them, but because they were never truly separate to begin with. This is what Einstein famously referred to as spooky action at a distance. He deeply disliked the idea, believing it pointed to an incompleteness in the theory. Yet over decades, experiments have consistently shown that entanglement is real, and in many ways, even more powerful than originally imagined. What quantum pseudo-telepathy reveals is that this connection is not just strange. It can be exploited. It allows participants to accomplish tasks that would otherwise be impossible, and it compels us to confront some deeply unsettling questions. Is the universe genuinely local? That is, does information only travel through space at a limited speed, such as the speed of light? Or is there something deeper beneath the surface, a hidden layer where distance and space themselves lose their meaning? Is realism actually valid? Do objects possess definite properties when no one is observing them? Or do those properties only crystallize at the moment of measurement? These are profound questions, and quantum pseudo-telepathy sits squarely at their center. This is not science fiction. It is not a clever illusion. It is an authentic feature of the quantum universe, one that appears to blur the boundary between what is separate and what is connected, between what is local and what is global. Some physicists interpret this by suggesting that reality is fundamentally non-local. Others argue that entanglement reflects a shared form of information that is not constrained by space. Still others believe it forces us to rethink what we even mean by reality itself. But regardless of interpretation, one fact remains. Two people can coordinate their responses perfectly without exchanging any messages, simply by measuring quantum particles in the correct way. It resembles telepathy. It feels like a violation of the rules, yet it is not. It is quantum mechanics. And the more you dwell on it, the more unsettling it becomes. Because if two people can act in perfect synchrony without sharing any information at all, then what else in the universe might be linked in ways we cannot perceive? There is a quantum experiment that sounds so absurd it almost feels like a joke. Imagine watching a cat walk along a corridor, but instead of seeing the entire animal, you observe the body heading in one direction while the grin drifts off in another. The smile floats freely, detached from the face of the cat. This bizarre image captures the essence of the quantum Cheshire cat. It is a real experiment, using real particles, that appears to separate a particle from one of its own properties. To grasp just how strange this is, we need to understand what the experiment is actually doing. In classical physics, an object and its properties always travel together. If you pick up a spinning top and move it from one table to another, you do not expect its spin to remain behind. The spin moves with the top. Its position and its rotation are inseparable aspects of the same object. But in the quantum realm, this intuitive assumption begins to unravel. In the quantum Cheshire cat experiment, researchers work with neutrons, extremely small particles that possess both position and a property known as spin. Spin is not literal rotation like that of a top. It is a fundamental quantum characteristic that helps describe how a particle behaves. It plays a crucial role because it determines how particles interact with magnetic fields and with one another. The experiment makes use of a device called an interferometer. This instrument divides the path of a neutron into two possible routes, much like a fork in the road. The neutron is placed into a superposition, meaning it does not take just one path. It exists in both paths simultaneously until a measurement is performed. Up to this point, this is familiar quantum strangeness. But this is where things become truly unsettling. In this setup, the system is arranged so that the position of the neutron is measured in one arm of the interferometer, while the spin is measured in the other. What the scientists observe is that the neutron behaves as though it travels along one path, while its spin appears to be detected along the other. It is as if the particle goes left, while its spin goes right. How can that possibly make sense? It should not, if we think of the neutron and its spin as a single, inseparable entity. In classical terms, this would be like separating an object from its mass, or pulling heat away from a flame while leaving the fire behind. Yet in this experiment, the results indicate that the particle and one of its defining properties, its spin, can occupy different locations at the same time. This is not an accident, nor a flaw in the setup. The measurements are performed with extraordinary care. They rely on a technique known as weak measurement. In quantum physics, there exists a technique that allows us to learn about a system without forcing it to surrender its full quantum nature. Rather than compelling a particle to commit to a single path or a definite value of spin, weak measurements offer something far gentler. They provide a faint statistical whisper about what may be happening, while leaving the superposition largely intact. When enough of these delicate measurements are gathered, an unexpected picture begins to emerge, one that seems to say, the particle traveled along this route, yet its spin appeared somewhere else entirely. This is what physicists refer to as a paradox, not because the mathematics fails or because the equations are incomplete, but because it collides head-on with our everyday intuition about how reality ought to behave. If the properties of a particle can be teased away from the particle itself, then we are forced to ask a deeper question. What does it actually mean for something to be an object? Is a neutron truly a solid entity moving smoothly through space? Or is it better described as a bundle of quantum properties that can separate, drift, and later recombine. Some interpretations of quantum mechanics argue that this is nothing more than a subtle measurement effect. From this perspective, nothing literally splits apart. What we observe is an illusion created by the way probabilities and measurements interact. Others, however, take the result at face value. They suggest that this experiment reveals something profound. Quantum systems do not possess fixed identities in the way classical objects do. A particle is not a tiny bead with attributes like position and spin permanently attached. Instead, it resembles a cloud of potentialities, and under certain conditions, those potentialities can move independently. That realization carries serious consequences for how we define the very nature of a particle. If position and spin can be peeled away from one another, it is natural to wonder what else might be separable. Could other properties be isolated as well? Is it possible to draw out charge without mass, or energy without momentum? The quantum Cheshire Cat experiment does not provide answers to these questions, but it invites us to ask them. It challenges the comforting idea that physical objects are solid and indivisible. In the quantum realm, that assumption does not always hold. It also forces us to reconsider what we mean by measurement itself. If what you observe depends on how and where you choose to look, then reality begins to resemble a shifting narrative. Objects no longer exist in a fixed, absolute sense. They acquire meaning only through interaction. This experiment also echoes, in a curious way, the logic behind the Wigner's friend paradox. In both situations, the message is the same. Reality is not simply waiting out there to be uncovered. It is shaped through the act of interaction. A particle does not carry its properties around like items packed in a suitcase. Those properties unfold according to the context of the measurement. So, if you ever felt that quantum mechanics had already reached the limits of strangeness, remember that there is a real experiment in which a particle's property seems to wander off on its own. The mathematics supports it, and the measurements confirm it. It is not merely a metaphor. In the quantum world, you really can encounter the grin without the cat. There is another quantum thought experiment that carries this strangeness beyond laboratory equipment and into something deeply personal. It is not just about particles and detectors. It touches on consciousness, survival, and the unsettling possibility that, from your own perspective, you might never actually die. This idea is known as the quantum suicide thought experiment, and it rests on one of the most radical interpretations of quantum mechanics, the many worlds interpretation. The core idea of many worlds is simple, yet profoundly unsettling. Every time a quantum event occurs, whenever there are multiple possible outcomes, the universe does not select just one. Instead, it branches. Every outcome takes place, each in its own version of reality. Rather than the wave function collapsing into a single result, reality splits into all possible paths. You only ever experience one of them. Now comes the twist. Imagine a scenario involving a quantum-based trigger, a device that produces one of two outcomes at random, each with equal likelihood. Picture, for instance, a quantum gun with a 50% chance of firing when a button is pressed, depending on the spin of a particle. The trigger is connected to a perfectly isolated box, sealed from any outside observer. No one beyond the box can know what happens inside. Only the person within is aware of the result. Now suppose that person sits inside and presses the button over and over again. In half of the universes, the gun fires and the person dies. In the other half, the gun does not fire and the person survives. Here is where things become truly strange. From the point of view of the person's own conscious experience, they always find themselves in the branch where they survive. The odds may be vanishingly small, but there is always at least one branch in which they remain alive, and their stream of consciousness continues within that version of reality. This leads to the idea known as quantum immortality. It suggests that conscious experience can only ever persist in those universes where survival occurs, regardless of how improbable those outcomes may be. To be absolutely clear, this is not a claim that people can live forever in the ordinary world. From the perspective of everyone watching from the outside, the person in the box dies in roughly half of the trials. That is exactly what external observers would record. Yet, from the first-person perspective of the individual inside the box, there is never a moment where experience simply stops. They never encounter the branch in which they are gone. Their awareness continues, always aligned with the version of reality in which they survive. They always awaken only in those versions of reality where they remain alive. That is where the paradox truly resides. Not in the machinery of the experiment itself, but in the character of consciousness. What does it actually mean to experience an event if every possible version of you exists somewhere in the branching structure of reality? What gives your particular stream of awareness its uniqueness? Why do you find yourself here, in this precise version of events, rather than in any of the countless alternatives? The quantum suicide thought experiment introduces no new physics at all. It takes established ideas from quantum theory, especially the many worlds interpretation, and asks what happens when those ideas are applied to a conscious observer who dies in one branch and survives in another. It is not an experiment anyone can physically perform because it depends entirely on subjective experience. Yet as a thought experiment, it pushes us into territory that extends beyond physics alone. One of the central issues it raises is observer selection. You can imagine vast numbers of copies of yourself, branching endlessly in different directions with every quantum outcome, but you do not experience all of them. You experience only the one that aligns with your internal sense of time. Your memories, your thoughts, your awareness. Survival in this framework does not mean you live forever in the shared world that others observe. It means that your inner experience never ends because it always follows the branch in which it continues. At first, that idea might sound comforting, even reassuring, but when you think more carefully, its implications become deeply unsettling. It suggests that no matter how unlikely survival may be, there will always exist one universe where you just manage to endure. Perhaps you are the sole survivor. Perhaps you are injured or isolated. Perhaps everything else has collapsed, yet you persist. That is not a triumph. It is something far more troubling. If your awareness always traces the surviving path, no matter how improbable, you could find yourself trapped in increasingly unlikely circumstances each time you survive. It may not feel like victory at all. From the standpoint of physics, this remains only one interpretation among many. Not everyone accepts the many worlds picture, and many physicists are unconvinced that consciousness operates in this way. Still, it is a natural consequence if one takes many worlds seriously and asks how it applies to the observer. It also exposes how little we truly understand about the role of observation in quantum mechanics. We can describe particles and probabilities with extraordinary precision, yet we do not fully grasp what observation means when it is bound to a conscious mind. Most interpretations attempt to sidestep this problem or smooth it over. Quantum suicide does not allow that. It forces us to confront the link between physics and subjective experience directly. That is why it is both compelling and disturbing. It is not about altering the laws of nature or constructing machines. It is about asking what it is that continues when everything else changes. What happens when the formal structure of physics collides with personal experience? The quantum suicide paradox provides no resolution. It simply opens a door that many never realized existed. And once you pass through it, a quiet question lingers. Is the version of me here and now merely the fortunate one that has survived this far? Among all the structures in the universe, black holes may be the most enigmatic of all. They are extreme in every sense. Gravity becomes overwhelming, density reaches astonishing levels, and even time behaves in unfamiliar ways nearby. Yet beyond the drama of event horizons and warped space-time, black holes have given rise to one of the most profound paradoxes in theoretical physics. It is known as the black hole information paradox. At its heart lies a deep conflict between two of our most successful theories, general relativity and quantum mechanics. To understand it, we must begin with what a black hole actually is. When a massive star exhausts its nuclear fuel, it can collapse under the force of its own gravity. If that collapse is sufficiently intense, all of the matter is compressed into an extraordinarily small region known as a singularity. Surrounding it is the event horizon, a boundary where gravity is so strong that not even light can escape. Once anything crosses that threshold, it is lost forever. At least, that is the description given by general relativity. In this theory, black holes are remarkably simple objects. They can be fully characterized by just a few properties: mass, charge, and spin. Everything else about what fell in, the structure of the star, the nature of the matter, the arrangement of atoms, is erased. It is as though the black hole forgets its past entirely. From the outside, all that remains accessible are a handful of basic quantities. Here is where the problem arises. In quantum mechanics, information is never destroyed. When a process occurs in a quantum system, information about the state is always preserved, even if it becomes dispersed or highly scrambled. This is not a philosophical preference. It is a foundational principle embedded in the mathematics of the theory. It underpins how probability functions in quantum mechanics. If information could simply vanish, the equations would fail. You would no longer be able to trace outcomes backward or make reliable predictions. So what happens when something falls into a black hole? General relativity tells us it disappears. Quantum mechanics insists the information must still exist in some form. That contradiction is the paradox. The puzzle deepened further in the 1970 seconds, when it was discovered that black holes are not entirely black after all. Because of quantum effects right at the edge of a black hole, near what we call the event horizon, black holes are not completely silent. They emit a faint glow, a whisper of energy known as Hawking radiation. This radiation is extraordinarily weak, almost impossible to detect, but given an unimaginably long span of time, it has a profound consequence. The black hole slowly loses mass. It shrinks, and eventually, after ages far longer than the current age of the universe, it evaporates completely. But here is where things become deeply troubling. Hawking radiation appears to be entirely random. It carries no obvious imprint, no recognizable trace of the matter and energy that fell into the black hole in the first place. If the black hole vanishes, and the radiation never encoded that information, then a simple but devastating question arises. Where did the information go? It cannot end up in the singularity, because the singularity is causally disconnected from the rest of the universe. It cannot be hiding in the radiation, because Hawking's original calculations tell us it is not there. And yet quantum mechanics insists that information can never be truly destroyed. It can be scrambled, transformed, dispersed, but not erased. Something, somewhere, has to give. This is not a minor technical disagreement. It is a head-on collision between two of the most successful theories ever constructed. General relativity describes gravity and the large-scale structure of the cosmos with astonishing accuracy. Quantum mechanics governs the smallest scales, atoms, particles, and forces, and it works with equal precision. Each theory is spectacularly successful in its own territory, but when they are forced to operate together in extreme environments like black holes, they fundamentally disagree. So far, we do not have a complete theory capable of reconciling this conflict. Over the decades, physicists have proposed a number of possible resolutions. One idea suggests that the information really is contained in the Hawking radiation after all, but in an extraordinarily subtle way. It may be encoded through delicate correlations that we simply do not yet know how to read. If that is true, then with perfect knowledge of the radiation and unlimited computational power, it would, in principle, be possible to reconstruct everything that ever fell into the black hole. Quantum mechanics would be saved. The difficulty is that proving this is immensely challenging because the decoding would be staggeringly complex. Another powerful idea is known as the holographic principle. It proposes that all the information inside a three-dimensional region of space can be fully described by information stored on its two-dimensional boundary, rather like a hologram. When applied to black holes, this suggests that everything falling in is somehow recorded on the event horizon itself. The horizon becomes an information-bearing surface. As the black hole evaporates, that information slowly leaks back out, concealed within the radiation. This idea emerged from string theory and has gained strong support within parts of the physics community. Then there is the firewall paradox. This proposal argues that if information is truly preserved, the region just outside the event horizon cannot be smooth and uneventful, as general relativity predicts. Instead, it would be violently energetic. Anything approaching the horizon would encounter a searing wall of particles, a firewall. That would solve the information problem, but it comes at a heavy cost. It violates one of the central principles of relativity, the idea that crossing the event horizon should feel no different from drifting through empty space, at least until you reach the singularity. Every proposed solution fixes one problem while breaking something else. And that is precisely what gives this paradox its power. It tells us, quite clearly, that we are missing something fundamental. Perhaps we need a new theory of gravity. Perhaps we need a deeper understanding of space and time. Or perhaps we need to rethink what information itself really means. It is also important to recognize that we cannot directly test these ideas. We cannot throw objects into black holes and patiently watch them evaporate over billions of years. Instead, physicists look for indirect clues. They study quantum entanglement, the flow of information in extreme systems, and even laboratory analogues. Some researchers create tiny black hole-like systems using Bose-Einstein condensate, searching for hints that similar principles might be at work. The black hole information paradox seems simple at first glance. Where does the information go? But the moment you try to answer it, you discover that it reaches into every corner of modern physics. Quantum theory, gravity, time, causality, entropy, even the nature of reality itself. This is not just a puzzle about black holes, it is a puzzle about the universe. And until it is resolved, there will always be a limit to how deeply we truly understand the cosmos. If you were forced to choose a single concept at the heart of all quantum strangeness, it would not be particles or equations or even time itself. It would be something far more familiar. Measurement. On the surface, measurement sounds simple. You look at something, you record its position, its speed, its state. But in quantum mechanics, measurement is not passive. It is not like checking the temperature or glancing at a clock. In the quantum world, the act of measurement actively changes the system being observed. This is known as the measurement problem, and it remains one of the deepest open questions in physics. To see why, consider an electron. Before you measure it, the electron does not have a single, well-defined position or speed. Instead, it is described by a wave function, a mathematical expression that represents a spread of possibilities. The electron is not here or there. It is not in one state or another. It exists in many states at once. This is what we call superposition. Yet the instant you perform a measurement, for example by checking the electron's position, you do not observe a haze of probabilities. You see one definite outcome, one position, one result. The wave function resolves itself, and the particle settles on one side. Not because that outcome was secretly fixed all along and we simply lacked the information, but because the very act of measurement compels the system to commit to a single result. The difficulty is that the theory itself never truly tells us how or why that commitment occurs. The mathematics lays out the probabilities with extraordinary precision and describes how the wave function evolves smoothly through time, yet it remains silent on the moment when those probabilities abruptly crystallize into one definite outcome. That silence is the heart of the measurement problem. So what, precisely, qualifies as a measurement? What is it that drives a quantum system to abandon superposition and arrive at one outcome rather than continuing to exist as many possibilities at once? Nowhere in the equations is there an internal rule that declares when this transition must happen. In the laboratory, we casually say that a detector or an observer has measured the system. But what genuinely changed at that moment? Did the wave function collapse simply because a machine registered a signal? Does it require a conscious observer to look at the result? Or is the idea of collapse itself a convenient illusion, something that emerges when a quantum system interacts with the wider world? Over the years, physicists have proposed a range of interpretations in an attempt to make sense of this. The Copenhagen interpretation, perhaps the most familiar of them all, argues that quantum systems possess no definite properties until they are observed. According to this view, Measurement itself brings about the collapse, yet it never truly explains what measurement actually is. It simply asserts that something about observation or interaction forces the system to choose. In contrast, the many worlds interpretation claims that the wave function never collapses at all. Every possible outcome occurs, each unfolding into its own distinct branch of the universe. Measurement, in this picture, is merely the moment at which your particular version of reality diverges and you find yourself experiencing one branch among many. But this immediately opens the door to further puzzles. What determines which branch you experience? Why does it feel as though only one outcome occurred if, in some deeper sense, they all did? Another approach is decoherence, which focuses on the interaction between quantum systems and their environment. It suggests that when a quantum object encounters the larger world, air molecules, light, anything at all, it rapidly loses its quantum coherence and begins to behave in a classical way. In this sense, the environment performs the measurement without any need for a human observer or even a conventional detector. Yet decoherence, for all its strengths, does not fully close the case. It explains how interference between possibilities disappears, but it does not explain why only one outcome becomes real in our experience. Then there are objective collapse theories, which propose that collapse is not triggered by measurement at all. Instead, it is a genuine physical process, something that happens spontaneously, much like radioactive decay. In these models, large systems cannot remain in superposition indefinitely. Given enough time, they collapse on their own. However, no one has yet observed this process directly, and the precise mechanism behind it remains elusive. Finally, there is the more radical suggestion that consciousness itself plays a role, that a system collapses only when it is observed by a conscious mind. This idea is among the most hotly debated and is often criticized for being too vague or drifting into philosophy rather than physics. And yet, it continues to resurface, largely because no one has managed to provide a more convincing explanation for why reality seems to become definite only when it is observed. Whichever interpretation you favor, the fundamental problem does not go away. We know that quantum systems behave in profoundly counterintuitive ways prior to measurement. We know that after measurement, we obtain a single, unambiguous result. But what transforms one situation into the other? The measurement problem matters because it is not a minor technical detail. It strikes at the very way we define reality itself. Is the world always there, complete with fixed properties, even when no one is looking? Or is reality something more fluid, a process that becomes concrete only through observation? In classical physics, the observer stands apart from the system. You can examine a star, a planet, or a cloud of gas without altering its essential nature. In quantum mechanics, that separation dissolves. The boundary between observer and system becomes indistinct. The act of interaction itself changes what the particle is. This undermines the traditional notion of objectivity in science. It is why some physicists argue that quantum mechanics, for all its success, is incomplete. Not because the mathematics fails, it works astonishingly well, but because it does not reveal what is truly happening beneath the surface. It offers predictions, not explanations. It tells us what we will see, but not why we see it. And so the measurement problem persists, not for lack of effort, but because every proposed solution seems to generate new questions. If measurement causes collapse, then what exactly qualifies as a measurement? If it does not, then why do we ever observe only a single outcome? If all outcomes exist simultaneously, why is our experience confined to just one? These are not merely technical puzzles, they are philosophical and foundational, touching the core of how we understand existence itself. Until we grasp what measurement really means within quantum mechanics, we cannot fully understand what the theory is telling us about the world. And perhaps, just perhaps, we cannot fully understand ourselves either. After navigating paradox after paradox, a pattern becomes hard to ignore. Each one gestures toward a different mystery. Some involve time, others observation, space, causality, or information. Yet they all converge on the same unsettling realization. our understanding of reality remains incomplete. Quantum mechanics is not an obscure curiosity tucked away in the margins of science. It is the framework upon which our description of the universe at its smallest scales is built, and it works. Its predictions are precise. Its experiments are repeatable. Entire technologies rest upon it: lasers, semiconductors, quantum computers. But the moment we ask what the theory truly means, we encounter questions we cannot yet answer. Every paradox we have examined is not a trivial oddity or a rare exception. It is a signpost pointing towards something deeper, something that does not quite fit within the picture we have constructed. The quantum eraser hints that time may not flow in only one direction. Wigner's friend suggests that reality itself may not be the same for everyone. Retrocausality unsettles our most basic intuition about cause and effect. Ideas such as pseudo-telepathy and quantum entanglement reveal connections between entities that, by everyday logic, should have no relationship at all. Experiments like the quantum Cheshire cat further erode the distinction between an object and its attributes. And then there are thought experiments such as quantum suicide, which push the questions far beyond particles and forces and turn them back on ourselves. Alongside this, the black hole information paradox exposes a deep tension between two of our strongest frameworks, quantum mechanics and general relativity. These theories are not merely in mild disagreement, they are constructed in fundamentally different ways, as if they are describing the universe in incompatible dialects. At the heart of all these puzzles lies the measurement problem, a persistent reminder that we still do not understand how potential becomes fact. We are remarkably good at calculating probabilities, forecasting statistical patterns, and describing states of superposition. Yet we cannot say why, when a measurement is made, one particular outcome emerges instead of another. When these threads are woven together, they form more than a catalogue of unresolved questions. They point toward a deeper conclusion. Our present understanding of reality is almost certainly provisional. That does not mean quantum mechanics has failed. It works extraordinarily well. But it may not be the complete story. Or perhaps it is already telling us something profound, and we have not yet learned how to listen properly. The mathematics tells us how events unfold, but the reason they unfold that way remains elusive. That missing explanation matters, because it reaches far beyond laboratories and equations. It shapes how we think about existence itself. Do we inhabit a universe that exists entirely independently of us, governed by immutable laws? Or are we participants in a reality that is, at some fundamental level, influenced by our engagement with it? This is not merely a philosophical curiosity, it has practical consequences. If observation plays a role in determining outcomes, then the observer becomes part of the scientific description, not in a mystical sense, but as an essential component of the theory. Perhaps consciousness is not simply a passive witness. Perhaps it is woven into the process by which reality takes form. Unsurprisingly, this idea is contentious. Physicists are deeply divided. Some expect that these apparent contradictions will vanish once a deeper, more elegant theory unifies quantum mechanics with gravity. Others argue that the paradoxes are signposts indicating that our entire conceptual framework needs revision, a framework that no longer depends on fixed space, linear time, or even an objective reality defined independently of observation. There is also an increasing awareness that we may be nearing the limits of what our existing tools can describe, not because the universe is deliberately obscured, but because we are still trying to explain it using concepts designed for a far simpler picture of nature. Newton described a mechanical cosmos. Einstein reimagined it as a geometric one. Quantum mechanics introduced a universe governed by probability. But the next step may be something even more abstract. It may be that the universe is not fundamentally composed of particles, fields, or even space-time itself, but of something we have yet to properly identify. This is precisely why paradoxes matter. They are not defects in our theories. They are guides. They show us where understanding ends and where new insight might begin. Many of the greatest advances in physics began as paradoxes. Newton's laws emerged from puzzles about planetary motion. Relativity arose from contradictions in electromagnetism. Quantum theory itself was born when classical physics failed to explain black-body radiation and the photoelectric effect. In each case, the paradox was not an error to be discarded, but a doorway to a deeper and more accurate description of reality. It is entirely possible that we are standing at such a threshold once again. We may be approaching a new kind of physics, one that explains why the quantum world appears as it does, not only in mathematical terms, but in conceptual ones as well. A theory capable of unifying the strange pieces: superposition, entanglement, non-locality, time loops, black holes, and the role of the observer. We do not yet know what form that theory will take. It may be hidden within string theory. It may emerge from the mathematics of quantum gravity, or it may arise from an idea no one has yet imagined. If such a theory exists, it must explain not just how the universe behaves, but why it behaves that way. Until then, we rely on a framework that is extraordinarily successful, yet deeply unsettling. It leaves us with questions about reality, identity, observation, and time. Questions that science alone may not yet be equipped to answer. Perhaps the most honest place to pause is not with solutions, but with recognition. Recognition that, despite everything we have learned, we are still gazing into the unknown, still pursuing something just beyond our grasp, still wondering whether the universe exists entirely on its own, or whether it is, in some subtle way, responding to the fact that we are here, watching it.